Thank you very much for the invitation to come to talk here and for that introduction. I'd like to talk about defending lives and housing against lava flows, an important geological and geophysical spreading to link in with the introduction. And I'm going to tell you about some theory and some experiments to back up the theory and a little bit about field data. I've done this work with enormous help from Ed Hinton, at the time graduate student, but now a postdoc in Melbourne, Andrew Hogg, who about 25 years ago was my graduate student, but now is a professor at Bristol, and Jack Saville, a new summer student who's working with me this summer. This is just so that you see the people involved, photos of Ed Hinton, Andrew Hogg, Jack Saville, and myself. Now, about 2,000 people have been killed by lava flows just in the last 20 years. So it clearly can have quite some damaging aspects. It also has destroyed much housing, and just what you want to do to prevent that is part of what I'm going to talk about today. What I'd like to do is to start with a little bit of an introduction, and part I've already given that, tell you about the mathematics, the mathematical setup, tell you about some experimental confirmation. I'll tell you some field data, but unfortunately the field data is not as extensive as I would like, mainly due to the pandemic, because I started working on this just before, and then I'll give you some take-home messages. The different situations that we'll talk about and the consequences are, first of all, simplified one-dimensional topography. And that's simplified in that it's easier to look at mathematically and to understand. But of course, the lava flow must overrun such topography if it's one-dimensional. And it can pond. It need not all go over, and it can form a pond. And what are the circumstances under which it forms a rather deep pond of magma? And that's what I'm going to talk about. Then we'll look at axisymmetric, rather simplified topography. When does it overrun? When does it go around? And when does it form dry patches? As we'll see, it's possible for areas of the ground not to be affected by lava. And so if it's a topography, that's where you're safe. But if it's a house, that's where you might run out and find out where again you'll be safe, which would be worthwhile. I'll then tell you a little bit about some experiments with the tall cylinder. The advantage of a tall cylinder, it can't be over top, but you can do that in the laboratory and get some interesting results. Easiest in the lab, as I've written here. And when there are dry patches, that's again the important thing, because that's where it's safe. Then we'll consider what the influence of a long defensive wall is, and we'll look at the force on the wall, because you want to build the wall so it's strong enough to resist the lava flow. And then I'll tell you something about depressions, which is the work of Jack Saville that we're just doing now. They're somewhat different, and they focus the flows. These are nonlinear flows, and so a negative topography is not just the same as a positive topography, only with a different sign. It's really quite different. Well, if we start now with a steady flow example, we have a line source, as you see on the top left, of lava, viscous fluid flowing over isolated mound, as I've used here just for the drawing, and we'll use as beta the angle of the incline over which the lava is flowing. And what we see is, as depicted in B1, it can all overtop the topography and bury it all, or as we see in C1, it can just flow around the topography and leave some of it exposed. We're going to analyze that by looking at the flow at far upstream, being capital H sub infinity is the thickness. We'll want to know how it varies downstream, which is X, and Y stream, Y, which is cross stream. And so that's the thickness H of the flow as a function of X and Y, and they're capitals here because they're dimensional. Soon we'll make it dimensionless. And then there's the height of the topography indicated by capital D, and then the non-dimensional height of the mound will be M as a function of X and Y. And as we see in B2, it can flow over, just like in B1, or in C2, it can leave a region that is not affected. Now, a constant flux of Q per unit width means that the height, H sub infinity, is given by this expression here, which involves the dynamic viscosity of the flow, the lava, the flux per unit width, the difference in density between the lava and the atmosphere, that's basically the density of the lava, gravity, and the sine of that angle. And I'm sorry, but it tells me what the time is here. And this expression is also valid for a slowly changing flux. Now, I'm just going to present the mathematics here quickly. I'm going to give you the interpretations mainly than bothering you with the mathematics. Just saying, if we non-dimensionalize to get little variables with respect to a length scale capital N and a thickness scale capital H infinity and a time given by all of those, we get, as you see on the second line, a rather complicated nonlinear partial differential equation. There are variations in both time and in position, both X and Y. And you see the gradient works on H cubed. And there are two non-dimensional and important parameters, curly F and curly M. And I apologize that they're the parameters that I use. They're the ones that were introduced by the graduate student Ed Hinton. They're not the ones that I would do, but now he's written everything, and on the I use his. F, I always remember it because of fire hose. It shows you H, that what it's telling you about the upstream dimensionless upstream depth, suitably non-dimensionalized, and the other variable script M, which I remember as medical doctor. That's my hint. D being the height of the topography. So if we increase M but keep F constant, that means that the flow is remaining the same, but we're making the topography higher and higher. Okay, first the simple situation where the topography only varies in one dimension. Then there are two things that can happen. For sufficiently small m, less than some critical value mc, so that means sufficiently, it's medical doctor, sufficiently small topographic heights, the flow all goes over in a nice smooth way, as you see on the bottom left. But when the m is greater than the mc, you have flow ponding, and it stays upstream of the height of the topography. So we want to know when that happens. In that simple one-dimensional case, the differential equation is still nonlinear, and we'll look at it time independent, but it's got this h cubed dh dx, and so there's some difficulties in solving it, but I'm not going to go through the mathematics. I'm just going to tell you about the results. This is now a proper two-dimensional topography given by e to the minus r squared. So it's a Gaussian distribution, if you like, in all directions from the top, which is indicated by the triangle. And you see y, what is normally the vertical axis, is across the stream, and down the stream is the x-axis. Now what you see for a relatively smaller value of m, 0.5, there are flow thicknesses that are positive all the way. On the other hand, if you increase the height by a factor of 3, in this case, that means m increases, it's 1.5, then you get a dry zone that is both at the top of the topography and downstream of the topography. H equals 0, i.e. there's no lava there. So if you like, that's a safe place. It's a safe place to put your furniture because it's not going to be affected by magma. Here are now the results, and as I said, I'm not going to concentrate on the details, I'm just going to tell you the results. For a flow around a cylinder, now this is a high cylinder, so M doesn't come into it, but curly F does, and it talks about the upstream depth or slope or cylinder radius. They all come into F. So the top one is the largest upstream depth, so it's really flowing, or the smallest slope, or the smallest cylinder radius. Then you see it's rather symmetrical. If we go down to the smallest value of F, 0.025, so that's a small non-dimensional upstream depth, a large slope or a large cylinder radius, then you see there's quite a large dry zone. So the difference in F, admittedly here by a factor of 100 or so, can make a big difference to the flow. So you need to know what the values are. Here's an experiment we did in the lab to check out what we were seeing. You see the flow going down from the left and going around this cylinder. We can calculate the force on the cylinder, and if F is very much larger than 1, you get one expression. If F is very much less than 1, you get a different expression. And I'll show you later references that you can look this all up. Now, here is a plot of the maximum and minimum depths upstream and downstream on the boundary of a cylinder. Simple case, a cylinder. The maximum depth will be upstream, the minimum depth will be downstream as a function of this parameter curly F. The actual numerical results are indicated by the red and the blue lines, and then we've done some asymptotic predictions for large values of capital F. And you see they're not bad after F is greater than about 4. But the numerics can be difficult, and if we extend them to topographies that are beyond the cylindrical, then it will clearly be difficult. Now, just 1 second. Can you do the chairs outside, if that's possible? Thank you very much. That would be good. Okay, so to continue, these are our results of the height of the flow as a function of F, and you see the experiments agree very well with the theory. So our nonlinear calculations are really quite good. Now, what about a square-shaped object? Well, here is the result for rather large values of F, where you see it not particularly interesting. The flow goes around everywhere. But here is lower down a small value of F, so that it means that it's going rather slowly to start with, thin far upstream, and then you see that there is a dry zone on the center line, roughly between 1 and 2.5. So that's quite dissimilar to the ones that I showed you for a cylinder. Okay, well, if that's what happens for a rectangle, what happens if we have a square and rotate it by 45 degrees? Well, that changes it quite a lot. And we're going to look at results, or we have, though I won't talk about them here, as a function of capital psi, the angle at which this square is with respect to the flow. Now, there are lots of further questions, which in fact, Jack Saville is going to look at this summer, my summer student. What shape of cross-sectional area A has the largest dry zone? If you want to build a building and you know what cross-sectional area it is, how do you put it, either place it if it's got a given area, or decide what shape it should be or what area it should be, so that you maximize the dry zone and make it as safe as possible. And then the question is, how does this depend on the input parameters? And they're good questions, and we're going to answer that if I'm invited again. In a real seminar, I often show this experiment of lava mimicked by viscous treacle flowing down past hotels and walls that you see here. And you see the dry zone that is formed by the hotel at the top, which is smaller than the hotel at the bottom, which seems not to have formed a dry zone. But it's not easy to do real live experiments in a Zoom seminar. Now, talking about walls, we can mimic a wall by looking at ellipses, because we can analyze that analytically. So the elliptical topography, where the lowercase b tells you, if you like, how elliptical it is. If b was equal to 1, it would be Gaussian and circular. If b is equal to 2, it's pretty elliptical. B is equal to 4, it's more elliptical. And you can see that from the streamlines. B equals 4 is going to capture quite a bit of the flow, as a wall is meant to do. Now, what about the force? The maximum force, if B is very large, so it really is a wall, is given by this expression, rho GL tan beta squared, which for a length of wall that's 50 meters, just as an example, and the slope, so that the tan of the slope is 1/4, the maximum force is the order of 10 to the 7th newtons per meter. And I always find it fascinating that I gave this seminar somewhere, I'm not going to say where, in a place that has important impact on lava flows. And the head said, my God, the force on the wall, I'd have never thought of that. And I felt like saying, and if you thought of it, you wouldn't have known how to calculate it, but I was a little better mannered. And another time I gave the seminar, somebody said, oh, Herbert, don't be stupid. Lava flows come so quickly, we'd never have time to build a wall. Well, of course, I didn't have in mind that we'd build the wall during the lava flow, but before. I went on a holiday before the pandemic in northern Scotland, and I couldn't resist taking a photograph of this sign, danger, unsafe walls, proceed at your own risk. There's not a problem, well, there wasn't a problem in northern Scotland because the volcanic activity there died away many tens of millions of years ago, but there are areas around the world where it is. Depressions are really quite different. Because it's a nonlinear situation, you don't just put in a minus sign and get a depression. Here's a Gaussian depression, and they focus the flow, as you see here, quite different to what would happen of the same values of F and script M, though it would be positive. Remember M, medical doctor, it's telling us about the depth. This is now a situation where there's both a depression and an elevation, where we're making the topography look like r squared e to the minus r squared. So there's a central depression, as I hope you can see from this three-dimensional green photograph, and it's surrounded by an elevation. What happens if it's the inverse of that, where it's elevation surrounded by a depression? We're just looking at right at the moment. But this particular case, no fluid can enter the central mound unless it overtops it. So that's really important. And what happens depends very much on the value of script M, And if it's less for this case than 1.7, the topography has nowhere an uphill situation, and the flow just goes around it and over the top of it. You get a pool formed if M lies between 1.7 and 2.5. And for this situation, if M is greater than 2.5, then you get dry zones. And the value of M will, of course, depend on the actual topography. These are showing you some flow profiles for different M's, and I see I spelled zone incorrectly. I'm terribly sorry. I'm having difficulty with the N on my computer. But for small values of script N, in other words, small values of the height of this topography, you get flow everywhere. But then as M builds up, you'll definitely get a dry zone. We've started to look at some aspects, how to compare this with real data, but that hasn't been as good as I would like, mainly because during the pandemic, people just don't seem to answer emails, and it's difficult to get hold of them. But we have done some work looking at some volcanic eruptions in Hawaii, and this is the beginnings, in a sense, of an eruption in May 2018. We've looked at the topography, solved the nonlinear equations numerically, and we get a reasonable agreement with the data here. There's much more data, field data, that we'd like to get hold of, and we haven't yet because of the pandemic. And that's why I put the field data agreements in small letter. So the take-home messages is that viscous flows, which simulate lava flows by considering them in the Newtonian limit, and I believe, and I can give you lots of examples where that is a good limit, where you can learn a lot. We can look at them numerically. We can get a lot of useful limits analytically, asymptotically, for a whole range of topographies. They can be two-dimensional, so that all the flow has to go over the topography. They can be axisymmetric. They can be elongated like they can have depressions and or elevations, or the two of them together. The agreement with somewhat special laboratory experiments looks very good, somewhat special because we've used cylinders, because that's the easiest to do, but we do envisage further experiments to be undertaken. We had that in mind when the pandemic started and all the labs were closed, but we hope to do that. This tells you something about me when I say agreement with field data is fantastic. The real truth is that the little bit of field data we've managed to get, there is good agreement, but there's lots more field data that can be obtained. But at the moment, I say it's fantastic. That's the best I can do. Here's some references if you'd like papers that have been written mainly by Ed Hinton, Andrew Hogg, and myself in the Journal of Fluid Mechanics, the beginnings of it in volume 876, the results of laboratory experiments in phys-rev fluids in 2020, and then the beginnings of the work over depression just a few months ago was written up and reported in the 22nd Australasian Fluid Mechanics Conference, which I wanted to get to, but of course couldn't because of the pandemic. And I was told that I might be invited to the 23rd Australian Fluid Mechanics Conference in December 2022, but the man who invited me said he's more likely to invite me than to be sure that I'll be able to get there. Australia is closed at the moment, as you, I'm sure, all know. Well, here's the flow and experiment in the background past a square that's at an angle, and you see the dry zone that has formed much downstream, the two blobs will link in together, and that will be the end of the dry zone. Okay, well, thank you very much for listening. And